So now that we have an ability to solve the non-homogeneous case for a higher order ODE, let's apply this knowledge to the example of a forced for an oscillator. In this case, because it's non-homogeneous, it will be forced. And first, we'll consider the situation of a non-damped force oscillator. I'll first derive the solution, and then we'll analyze the behavior of the solution for different driving frequencies. And the driving frequency is, we'll denote that as capital omega. And please write down this objective on the top of your notes. Your objective will be your ability to find the solution for a non-damped oscillator with a driving force of frequency omega, and to explain the behavior for different driving frequencies. So again, let's sort of sketch our harmonic oscillator, which we can visualize as a mass on a spring. It's attached to a fixed wall. And of course, we have a viscous fluid resisting the motion, and in this case we have a driving force, which is a function of time. So this is someone pulling and pushing on our mass with a force that changes with time. So the general equation again is mx double prime. So this is inertia. This is mass times acceleration, plus our viscous resistance, and this is our viscous damping term, plus the resistance of our spring, and that's equal to all terms that are independent of our position, which in this case is our driving force. So the situation without damping is in section 3.8.1, as I noted in the very first slide here. So this is no damping. So this is our non-damped oscillator. In which case our equation, let's rewrite this, leaving the second derivative by itself. So we'll divide each side by m, and we get k over mx is equal to f over m. And the form of our driving function is a cosine function. So this is our driving frequency. And we might visualize it as this is a cosine function, right, with amplitude f. So it goes from minus positive f0 to, it goes from minus f0 to positive f0, and the angular frequency is, well, the period is t, the x-axis here is little t, the period is capital T, and omega is equal to the number of a complete cycle in a full number of radians in a complete cycle. That's 2 pi over the period capital T. So we have now a second order ODE with constant coefficients, and we have this forcing function, which will have a non-homogeneous solution that we need to solve for. But before we do that, let's look at the homogeneous solution. To find the homogeneous solution, we set the right-hand side equal to 0 again. And remember, we assume that x sub h is proportional to e to the lambda t. And with that, we get the characteristic equation, lambda squared plus k over m times lambda. Oh, I'm sorry, there's no multiplication times lambda. It's just k over m is equal to 0. And that gives that lambda is equal to the square root of minus k over m. And so lambda is going to be imaginary, so it's I plus and minus the square root of k over m. And with an imaginary lambda, we get an oscillatory behavior. So we can write that oscillatory behavior as a sum of a cosine function plus a sine function, where the frequency of our oscillation, omega, was equal to the square root of kappa over m. The triple bars here mean, we're defining our natural frequency by this ratio, the square root of k over m. When we have triple bars, that means we're making a definition. And this is our natural frequency. It's the frequency that for a given spring constant and the size of our mass, it will naturally tend to oscillate without any driving force. And we looked at this solution before. So without any driving force, if we set the mass in motion and there's no viscous damping, then it will just oscillate with this natural frequency. Now, I'm just noticing that I didn't write this solution correctly. And some of you hopefully noticed this and had some questions on this. So if lambda is equal to the square root of minus km, then the solution for lambda is plus and minus I times the square root of km. So let me make sure we get this corrected. Plus and minus I times the square root of k over m. And when we raise e to the plus I square root of km and add that to e minus I times the square root of km, we can rewrite those two linearly independent functions in terms of the linearly independent functions cosine and sine. So let's rewrite this equation as x prime prime plus omega squared, that was k over m times x, and that's equal to our forcing function omega f naught cosine omega t. I'm sorry, this is capital omega now because our driving function is generally with a different frequency, and that's all over m. So we have a sort of 10-step process to solve for the non-homogeneous solution, right? So number one was to check if the coefficients were constants. And yes, they are. The second step was to determine if subsequent derivatives of the forcing function gives a finite set. So derivatives of f of t indeed give the finite set of cosine omega t, capital omega t, and sine capital omega t. And since it's finite, then we can proceed in solving for our non-homogeneous solution. Step number 3 was to identify the linearly independent set of functions So this was step number 3. And number 4 was to tentatively set the non-homogeneous solution equal to a linear combination of that set. So that's C cosine capital omega t plus D sine capital omega t. So this is our tentative solution. Step number 5. Step number 5 was to get our general solution. So we have xh. Again, our general solution is a cosine little omega t plus b sine little omega t. And number 6 was to check for duplication of terms. And we're comparing the particular solution or the non-homogeneous solution. I gotta make this a little bit more clear. So this is NH is the non-homogeneous solution, and we're comparing that to the homogeneous solution. And there are no duplications if little omega is distinct from capital omega. And so this is the case we are going to consider right now. So none of these, as long as these are different, then there's no duplication between cosine capital omega, for example, and cosine lowercase omega. So since there is no duplication, then we're done with step 6. We don't have to do any corrections to our tentative guess at the non-homogeneous solution. Step 7 was to substitute our non-homogeneous solution, x and h, into our ODE. And so we need a second derivative plus omega times x itself. And the second derivative is again, we're looking at this, the non-homogeneous solution. And so we get minus c omega squared, capital omega squared, cosine capital omega t, minus d omega squared sine capital omega t. And then we have to add that to lowercase omega squared times x itself, and that is c cosine capital omega t plus d sine capital omega t. And that's all equal to 0. Oops, I'm sorry, we're solving the complete non-homogeneous case, and that's all equal to capital F F naught over m times cosine capital omega t. So we need to collect like terms. And so let's collect the terms on the left-hand side proportional to cosine omega t. And we get capital C times little omega squared minus capital omega squared cosine capital omega t. And the terms proportional to sine are d times little omega squared minus capital omega squared sine capital omega t, and that's equal to F naught over m cosine capital omega t. And then 8 was to solve for our coefficients. And so if we compare, so we can see that we have two cosine omega t's, one on the left-hand side and one on the right-hand side. So comparing those terms, we see that c times little omega squared minus capital omega squared is equal to f naught over m, and therefore c is equal to f naught over m all over the difference in the two frequencies. So that's our first coefficient. And our second coefficient, since there's no sine function, we know that d is equal to 0. Now the ninth step was to repeat for other parts of the driving force. And in our case, there's only one driving force. And so we don't have to do that. And then 10 is to give the general solution. So the general solution, again, is x is equal to the homogeneous solution plus the non-homogeneous solution. And that's a cosine a little omega t plus b cosine b sine little omega t plus f naught over m times the difference in the two frequencies, the difference between the natural frequency and the driving frequency squared, times our oscillatory term for our driving force. And so this is one form of a general solution. We could equivalently write that as x is equal to e cosine omega t plus phi plus our non-homogeneous solution times our forcing function. And here the amplitude of our the cosine function on the natural oscillation, the unforced oscillation, is the square root of a squared plus b squared, and then phi, the phase shift, is equal to arctangent of a over b minus pi over 2. And the minus pi over 2 gives the cosine function. We derived this solution using a sine function, and so with the cosine function, we just have a slight adjustment to our definition of phi. So that's our general solution. So that was the derivation of our general solution. So now let's look at the behavior of our solution for different driving frequencies. So actually, the first thing to note before we get into driving frequencies is that as the response of our forcing function is directly proportional to the size of the force itself. So if we were to double the force by which we were to push on our mass, then the response would also double. And so this is an aspect of the linearity of our ODE. The response is directly proportional to the force. The other thing to notice is that the amplitude of our non-homogeneous solution is proportional to 1 over the difference between the natural frequency and the driving frequency. And remember, the natural frequency was the spring constant over m minus, and then, right, so omega squared is equal to k over m, our spring constant divided by m. So let's look at how the amplitude, so this is the amplitude of our response, and let's take the absolute value of that amplitude. So let's plot the absolute value of f naught over m over omega squared minus capital omega squared. So in this case, we'll keep little omega, the natural frequency, constant, and we're just going to look at the effects of varying the driving frequency. Right there. And there's a special point where the driving frequency is equal to the natural frequency, and we haven't produced that solution yet, but the behavior looks something like this. The maximum, or the amplitude of the frequency, as you can see with the difference being on the denominator, as capital omega approaches little omega, the amplitude shoots up to infinity. And it shoots up on both sides, where capital omega is less than the driving frequency and capital omega is greater than little omega. And so this on this side, it decays to 0. So the amplitude of the response also depends on the differences in these frequencies, and it blows up as the driving frequency approaches the natural frequency of the system. So let's look at the case when omega is equal to, little omega is equal to big omega. Or I should say, when we set our driving frequency equal to the natural frequency. And this is the situation where we have resonance. So remember, when we had our tentative solution for the non-homogeneous part, we had C cosine capital omega t, and remember, this is now equal to little omega t. And before, when the two were different, there was no redundancy in the terms between this and the homogeneous solution. But since now, so this is now redundant. With our homogeneous solution. So we have to multiply our non-homogeneous solution by the lowest power of t that removes the redundancy. So we get c times t cosine omega t plus dt sine omega t. And then we substitute that into our ODE and solve for the coefficients And when we do that, we get C is equal to 0, and D is equal to F naught over 2m omega. And the complete solution there, and the solution for our non-homogeneous solution becomes F naught over 2 omega m times t sine omega t. This again is when capital omega is equal to little m. And so if we were to plot that up, what you should notice is we have a periodic function, and the amplitude of the periodic function increases linearly with t. So the linear increase with t, so it starts off, the amplitude is 0, but as with t, the amplitude, well, x and h, the amplitude of the oscillation increases linearly, and so the full solution will look something like a sine function with increasing amplitude. And this continues to grow to infinity. So theoretically, the oscillation would get bigger and bigger and bigger. Of course, in reality, there'll be mechanical limitations to how big that can get, and this and that, for example, is what leads to the breakdown of buildings when for example, in an earthquake, if the earthquake shakes at the resonant frequency of a building. So that's one sort of case where resonance is a bad situation. There are also desirable effects of resonance in some that we exploit in some situations. One example is if in the case of tuning, where we tune our radio receiver to the broadcast frequency of a particular station we wish to listen to. Okay, so now we've looked at the sort of the case in which the driving frequency is equal to the natural frequency of the system. Let's go back to the case in which omega, the driving frequency, is distinct from the natural frequency. And let's find the particular solution for the initial conditions that x of 0 is equal to 0, and the velocity of our mass, the speed of our mass at time is equal to 0, is also equal to 0. And when so our general solution again was x is equal to e cosine little omega t plus phi plus f naught over m all over the difference in the squares of our two frequencies times cosine omega t. And using these initial conditions, we find that phi is equal to 0. That's the first constant. And the second constant, e, is equal to minus f naught over m over a little omega squared minus capital omega squared. And so this gives the solution, the particular solution, of x being equal to minus capital f naught over m over little omega squared minus capital omega squared times cosine little omega t minus cosine of our driving frequency times t. And using a trig identity that relates the sum of two cosines to the product of two sines, we get that x is equal to 2 f naught over m, all over the difference in the squares of our frequencies, times sine, a sine function whose frequency is the average of our natural and our driving frequency, and a function whose frequency is equal to the difference in our natural and driving frequency, or half the difference times t. And so we have two sine functions that modulate each other. And Greenberg shows various examples of functions, solutions, for different values of the driving frequency compared to the natural frequency. So in the top panel here, the driving frequency is much less than the natural frequency. So the driving frequency is this sort of long period oscillation, and it looks like a long period oscillation superimposed with a short period natural natural frequency. But he shows that as the two frequencies become closer and closer together, you get what's often called a beat sort of behavior, in which the function behaves as a short wavelength oscillation. In this case, this is the natural frequency being modulated by a longer wavelength oscillation caused by the driving force. And this sort of beat phenomena, I guess, is similar to if you've ever tuned an instrument. You're comparing the oscillation of the instrument with the tune that the note that you're trying to reach with it, and your ears are responding in a way to this the joint signals of those two, and you get this sort of beat sound when you listen to that. It's a very similar type of phenomenon. Certainly when the driving frequency gets very, very close to the natural frequency, you get a behavior that acts like resonance, again, with the shorter period oscillation, the amplitude of that growing and growing to very large amplitude with continued resonance. So you can see that for this one solution, we get a rich range of behaviors depending on the size of omega relative to size of the driving frequency compared to the natural frequency. And so this concludes the discussion of the forced non-damped oscillator.